Okay, so today we'll be looking at our first geometries here, and we'll start with this example here, the half moon tower. Many of these will probably look familiar to you guys because you've all seen them and worked on them before. You've taken the second year Rhino direct modeling studio, and in a way, it's purposeful because now that you already have a very clear idea of the procedure in terms of how it's modeled in a Rhino, I think it'll give you a bit of a better understanding of how that translates into modeling in parametric design tools like Grasshopper, which is built on Rhino itself. So let's see, what I would like to start with then is this half moon example, right? And so if we remember when we talked about that in our Rhino direct modeling class, um, it was, we were already kind of thinking about that process as a step-by-step nature, right? So we looked at things like creating the sphere, right, from the basic shape, cutting the sphere in half, and then translating them into different positions in space to create the final geometry, right? And so, with that kind of understanding, right, it allows us now to think about, well, if we're going step by step like that and working in a very procedural way, how would we, kind of mimic that process using the Grasshopper interface and our, our canvas, right? So the first thing that we did when we were modeling it directly, of course, was we created the geometry, right? So let's go ahead and start by creating a geometry. And in this case, we're going to go to our surface tab, right? And we're going to pick a sphere, right? Now, we have lots of different ways to create geometry, just like in Rhino, right? You have things like quad sphere, sphere 4-point, sphere fit, etc. And basically, the thing to realize is that oftentimes you'll have, multiple ways um, to create any of these things, but what's changing, right, is the types of inputs that it takes, right? So in this case, the sphere that I picked happened to take the input base and radius, right? And, if I had picked one of the other spheres, it would generate more or less the same thing, but you see the inputs are different, right? And here that also allows you to, find the center of the sphere or the radius of the sphere. Of course, we could also use our analysis tools, right? Connected to that and also get that same information from our sphere. It just so happens that when they developed this component, they thought it was necessary to include those into the component itself, right? So in this case, I think this sphere, the sphere that uses a base and a radius is kind of the the one that requires the least amount of additional information to work with at first. So we're going to start with that. And you'll notice that as soon as I kind of put this component out here, right away, a sphere appears, in my in my Rhino window, right? And again, this is an imaginary item, right? There's no geometry in my Rhino file yet. This is just a preview of what's happening here. So, all right. So right now we have this sphere here, right? But if we go back and we look at our geometry here, right? Again, we realize that actually, what we want in order to create this half moon tower is kind of four semi-spheres, right? So we're gonna have to find a way to kind of change this geometry to a geometry that's more useful to us. And in this case, if we had been working in Rhino, what we did, if you remember clearly, is that we created the sphere and then we used the kind of Boolean difference command to cut half of the sphere away, right? So if we follow the same logic, right, we could do the same thing using our intersect tab, right? So if you go to intersect in Grasshopper, you can see that we have here also these kind of Boolean components, right? So in this case, a solid difference, right, is the one we would pick because solid difference is the same as this one, right? Boolean difference. Okay, so you can see here that solid difference is expecting 2 reps, right? So a B rep is simply a representational geometry, right? NURBS geometry specifically. So here we have the sphere, right? That's going to be one of them, right? And then the other one is going to be our cutting object, right? So we haven't established a cutting object yet, right? So let me just do this quickly for you guys so you can remember. Perhaps some of you have forgotten how this works in Rhino, or may not have even taken that class, but I'm only going to do this for this one example. So it's super clear, right? So you have one original object and a second object that I'm using simply as a cutting object, right? And then I'm going to take my Boolean, I'm going to pick the object that I want to keep, enter, and then the object that I'm subtracting with, enter again, and you can see it made a cut through that object, right? So essentially what I'm doing is I'm doing the same thing here, right, in Grasshopper, except I'm writing it out step by step instead of doing those actions here, right? So what I'm missing is that second object that I'm going to use as a cutting object in order to do this Boolean operation, right? So that second object that I used, you could see, was a box basically, right? So we have here now the opportunity to look for another geometry that's suitable for the tasks I'm trying to do, right? And in this case, I'm looking for some kind of box, right? So again, you have various choices, right? And I'm going to choose this one called box rectangle, right? And so what this will do is create a box with 2 inputs, a rectangle input and a height input. Now, both of these, as you can see, are still giving me warnings, right? That's what that orange color indicates, if you remember from our lecture last time. Which means that it's unable to execute because it's missing something, right? Or, some of the data that I collected was, had some problems and it wasn't able to actually input into the process, right? And in this case, it's because by default, these are empty inputs, right? So because they haven't had anything put into them, they're unable to generate anything. Unlike the sphere, right? When we drop the sphere on the canvas, it automatically was, its normal color, right? It's kind of grayish gradient color. And that's because by default, right, it has values for its inputs, right? For the base, it has a world XY, and for the radius, it has a 1, right? So it, if for instance, there was no default value for this radius, then when you dropped it onto the canvas, it would also, do nothing on the screen and appear orange, right? Okay, so that means we need to start thinking about, well, how do we start to link these things up, and what kind of information are we missing in order to generate the result that we want, right? I would start with this box because it's earlier on in our chain, right? It's close, on the left side rather than on the right side. And what we're missing here are two things, basically, a value of a height as well as a rectangle, right? So you can see that, if these are your 2 inputs, then what it's really telling you is that, well, the way it's going to generate this box is with a curve, a rectangular curve, right? And extrusion, right, of a certain height. So let's go ahead and use a number slider for our height for now, right? I don't know exactly what it needs to be yet, but I'm just going to put a number slider in there. And then a rectangle here, obviously we're not going to be able to just use, a number slider input or any of these other ones. Really what you would need to do is to, maybe use a container, right? And you can import. But again, like I said, we're going to be, we're going to try to do this as explicitly as possible so that everything that's, generated is done here on the canvas rather than kind of working back and forth for at least, the first couple weeks of this course. So let's go and see what options we have in terms of generating a rectangle from within Grasshopper itself, right? So a rectangle we'd expect to find under our curve geometry, and maybe as a primitive, right? So when you look at our curve primitives, we scan through here and you can actually find one or a couple, or a few that are rectangles, right? And in this case, I'm going to use a rectangle that's constructed from 2 points, let's say. So this rectangle, you can see it appeared just like the sphere did in space here. Again, that's because there are already preset default values for the point A and point B, as well as the plane and radius, right? In this case, the radius refers to the corner of the rectangle. So the fact that it's set to a 0 radius means that they come to a sharp point. And then points A and B are simply the 2 points that define the external corners of that rectangle, right? So what you'll see is that those 2 points are a composite, right? It's not just a number like that you can control with a number slider. You can see the input data here is actually a coordinate in space with an x, y, and a z, right? And so since we can see that, that means that in order to, well, for one, we could accept the default values, right? But if we wanted to have control over the size and shape of this rectangle, we'd really need to be able to define that coordinate in space, right? So what is a coordinate? Well, coordinate is a point, right? So if we go to our vector tab and we go to point, you can see, well, there are a number of ways to work with points, and you can construct a point this way, right? Using a point component. So now you can see, okay, so I can make, well, I have 2 inputs here really. So I'm going to need probably more than 1 point. I'm going to go ahead and, well, before I copy it, actually, I'll wait. But you can see here that this point appeared as well, right here at our origin, because the default value of x, y, and z just happened to all be 0, right? Now, if I wanted to be able to control the location of this point, right, I could connect a slider to it, right? And you can see now in our Rhino screen that if I change the value of that slider, that point moves around in space, right? Of course, the range is quite limited right now, right? It's only moving between 0 and 1. So I'm going to change the range that is available on this slider to, let's just say 1 to 10. Okay, commit, but I also want to change the slider type to integer value only, right? So now you can see that point has a much larger range of motion, right? In fact, I think it would make sense to change this to a -10 as well, so that we can move in both directions, right? Now we can move backwards and forward on the x-axis, right? So if anyone's wondering, well, what's happening there, we can look at that specifically by turning on our panel. You can see that when I have that set to 0, right, and these are at the default 0 values, and I change that, you can see that what's being outputted, right, is this coordinate in space, right? So I can do this also for the y, right? And that would allow me to, create different values so that could move diagonally now. And I could also add one for z so that it could move, vertically in the 3rd direction. But since we're working with a 2-dimensional object, this rectangle here, I only really need to worry about the x and the y, and the z we're just going to ignore for now, right? So let's suppose that I now connect this point as point A, right? You can see what happened to our geometry is that now, right, we have one point, this one, which is being defined point A, in order to generate this rectangle. Point B hasn't changed. It's still stuck here at the default and is not really modifiable, but you can see now that I can, I have control of that second point that's generating it, right? So if I wanted that flexibility with the second point, I would simply select and then copy and paste that second segment to point B, right? And so now I have a rectangular geometry that, allows me a lot of kind of flexibility, right? In terms of, the result that I'm trying to get out this rectangle. So that rectangle goes to our box, right? And so now instead of just being a rectangle, a two-dimensional rectangle, it's being extruded in space to a certain height, right? Defined by this slider. Now, right now, because it's stuck in a certain range from 0 to 1, that means that I don't have the ability to make that box even big enough to cut through the size of that sphere. So I'm going to change the range on this slider that's connected to the height, and then that will allow me to create boxes that are, bigger and better for the task that I'm trying to do, which is essentially cutting um, that sphere, right? So you can see here that now, I actually have this box in a position that would allow me to intersect and cut through that sphere, right? However, and so you can imagine that, okay, that this is my, BREP B and this is my BREP A, right? And so the result, um, if I hide, right, the result is something like this, right? Because this box cuts through that much in its current size and shape, right? Of course, if I start to modify this, right, you can see that if I made it this way, right, then it only cuts out a quarter or an eighth rather, since there's top and bottom as well, of the actual sphere itself. But in our example, that half moon tower, actually what we want to do is cut away an entire half of that geometry, right? So in order to do that, actually, we have a couple options. One is we could move the position of this sphere, right? So that it doesn't intersect with, or so that it intersects better with this geometry here. Or we can move the box. And in this case, I'm going to use the box. So I'm going to go ahead and copy and paste that here. And then connect a z coordinate to those so that I can define that box on a lower z axis. And since I want it to be flat on the bottom, right, in order to maintain the rectangle, I'm going to go ahead and link um, this box. Actually, no, I want to move this sphere now into a position that's easier for this box to actually cut. So if I set this up like this, now instead of cutting a quarter of it away, I can simply change the position of this base, right? Which is currently world XY, which means at the origin, right? And I can use a move uh, to change the base of that sphere, right? And then move that sphere in such a way that I can get a better cut through there, right? To get half the geometry, which is what I'm looking for, right? Like this. So I'm going to go ahead and hide again the stuff that I don't need so I can just see the part that I'm interested in, right? Which is that one kind of hemisphere, right? Uh, and in our direct modeling session, after we had arrived at that hemisphere, what we did was we started to copy and paste, right? And then translate in space, right? In order to kind of get four of them that are opposite each other, right? So the thing is that right now we just said, oh, we would copy and paste it. But actually, what you realize is that in Grasshopper, because everything, again, like I mentioned in our first class, is continuously being processed and updated, right? Um, it doesn't really make sense to have a copying feature, right? And well, a copying feature and a move feature, right? So for instance, if I were to go to transform, right, and I chose move, right? So I take that geometry and I move it. And let's say I move it a certain direction uh, in the Z axis, right? Here it's already has a default of 10, so it's already way up there. But say unit Z and a factor of somewhere between -10 and 10, right? So I use the unit vector to define the direction that I want it to move, right? And that way I can leave that X and Y untouched very easily, right? So I can, for instance, adjust that motion, right? Now you'll notice that, well, when I moved it, actually the previous iteration, right, is still there in memory, right? And that's because you can see it in your definition in the step right before the original one. So instead of copying something, all you would need to really do is just leave the previous iteration there, right? Instead of going and hiding it, right? After you kind of moved on, right? And that would essentially mean that you had copied it in space, even though actually what you really did was just moved it, right? But now, in a way, what we're saying is that we're interested now in the future development of both of these geometries, right? Not just this one here, but something that happened previously in the chain, right? And what we would want to do now is essentially try to do a mirroring function, right? So that we could have those spheres facing the other way as well, right? So if we go down to our transform tab, we'll find that we can find a mirror component, right? And with the mirror component, I can simply say, well, define the direction, right, that we want to mirror the geometry. And you can see that there's a mirror plane here that appears. And I can tell right away that the plane is not oriented the right way, right? So I'll need to change the default plane to a different plane and then select the geometry that I want to mirror, right? So to define a plane, I would go to my vector tab, right? Go to plane. And I think this is a YZ. So let's see what a ZX, right? ZX looks like the plane that I want to mirror in. And then I'm going to go ahead and place my geometry holding shift so I can do both of them simultaneously, right? And you can see it mirrored that geometry onto the other side, right? Now, finally, I think the last step is, quite quite simple, right? I just want to move it again, right? So I'm going to go my transform to move. Select the geometry that I want to move from its original position, right? And so I will go ahead and select those two geometries and then put a slider so that I can determine the direction. Oh, I need a slider and a direction. So I need both the unit vector, copy paste. Right, and that will allow me then to move those two in any to any z position. Now, what you can see is that based on this division, I'm not able to kind of get it in the center, so I'm just going to turn off the integer value limitation, go back to floating point, and then that'll allow me to make more discrete movements. Then I can turn off or hide the previous generation, which would allow me to get like that as well. You know, the final geometry that's very similar to our worksheet, right? So we have 4 hemispheres, right? That look like they originally were 2 spheres cut in half and then offset, right? Like that. So as you can see, actually the workflow for modeling something in a Grasshopper tends to be quite a bit slower than using a direct modeling method like Rhino, especially when you're working on something where the geometry that you're trying to achieve is all very clear, is something you understand already. Um, and in that case, it may not make so much sense for you to use parametric methods to generate this type of geometry because it's so simple and so clear and easy to understand, right? But for the purposes of this training, for you guys to get familiar with the tool and comfortable using all the components and stuff, I think this is the best way to proceed. And later on, you'll be able to make a better judgment in terms of which method of modeling you use, whether it's direct modeling or parametric modeling based on certain cases, right? So an ideal situation where parametric modeling helps is if you have, lots and lots of geometry that has a lot of variety in it, that needs to be organized, that, you can't even really imagine the results of because it's far too complex for the human mind to look at that kind of raw data and try to interpret what that would result in formally, right? So, all right, that's our first example. Please take a little time and try that on your own, and we'll come back and go on to the next one. Okay, so in the next example, house, we will look at some other ways to work with our parametric tools. Uh, let's see. Okay, here we go. So in this example, actually the tricky thing is that we're kind of, if we go back and think about how we would have built this in Rhino, right? We probably would have drawn an outline of that house and what it looked like, right? And then we'd, create a second object again and use our Boolean tool to cut away the part of the geometry that's missing, right? So we know we're going to be working in this case with some curve tools, right? But it could be pretty tedious to try to plot points, right? So if we look back at that geometry again, you can see like there's, if we said, okay, we need this shape, right? We could go and, try to draw a curve, right? That looks just like this, right? But, if we look at our curve tools under spline, curve and spline, you can see that essentially they're more or less they more or less work the same way that the inputs work in Rhino, right? So if I select polyline, for instance, you can see, well, it just takes inputs of points, right? So if I have a whole bunch of points and I input it here, then it'll draw a line through all of those points, right? But what does that mean? Does that mean that we're going to come here and you're going to construct a point, right? And do that, copy paste 5 times? I mean, you could do that, right? And then move these sliders until that dot is in just the right spot, right? So that you can get a dot here, a dot here, a dot here, a dot here, and a dot here, right? And then draw a line through it. Yes, you could do it that way, but probably the easier way to do that would be maybe to stop for a minute and think about what this geometry is, right? So 5-sided geometry like this, now we can imagine actually is really more like 6-sided geometry, right? With one of the points missing, right? So if you imagine this is a hexagon now, right? But now you just deleted one of those points, then what you'd have left is basically this shape, right? So with that understanding, right, let's look at how a better way would be to generate that same result, right? So if we go to our curves, you can see that we actually have other, a lot of other tools, right? Including things that are for drawing shapes, right? And as we said, well, if we're able to create a polygon, then doesn't that make sense to start with, for instance, a 6-sided polygon, like maybe just like this, right? And if we look at it in this way, then maybe actually what we could do is think about, well, what if we, just pulled out the points that we want and only use the points that we need in order to make that drawing that we're looking for, right? So, if we look at this, we can see that, okay, here it's creating a polygon. And this polygon, if we go to our analysis tab, we can see that it has what? It has endpoints. Actually, more than 2. So we're going to use discontinuity instead, right? So what discontinuity will do will allow us to extract all the locations where this curve is no longer continuous, right? So basically it's multiple curves joining up at that point, right? So you can see here that now it has 6 points, right? So with 6 points, what we can do instead is now we can come into our sets, right? And we can start to look at what's happening and how we can modify it, right? So if we go under parameters, right, and we turn on a view of what is being output from our discontinuity, you can see that we have 6 points here, right, from 0 to 5, right? 1, 2, 3, 4, 5, 6, right? And all the locations of those points are indicated, right, as XYZ coordinates here in space. Now you could probably figure it out, like which point is what, right? This looks like, X3, right? And then Y and Z are both 0. So, that's 0 is here, right? And then 1 is in the positive direction, right? So I'm going to guess that means that this point is 1, 2, 3, 4, 5, right? You could do that, but again, that only works for very simple geometry. So we need a tool that'll help us to identify, right, which point actually belongs to which line in our data set, right? So to do that, we're going to go to display, and we're going to choose this one called point list, right? And point list will allow us to number all those points, or assign a number, that we can see visually here, right? Right now, the size is too small, so we're not seeing it. So we need to pick an appropriate size. Let's say 2 and see what happens. 2 is pretty big. Let's say 1. Yeah, and that's fine for what we're doing, right? Okay, so we see actually, so I had this completely turned around. And in fact, z x is in this direction. Which way is my z? Z, x, there we go. Okay, so I had that completely turned around, so the grid was completely wrong. But basically, this is our x direction, right? We can see down here. So this is the 0 point, right? Which is here. This is 1 up here, 2, 3, 4, and 5, right? And having these the point list, right, display them makes it much easier for you to figure out, okay, so which one of these then would I want to maybe omit in order to create that the geometry that I'm looking for, right? So if we say, okay, I want to create that shape this way, right? Then I want to omit number 3, right? Value 3 from my list, right? So to do that, we need to go into our sets, right? And we need to decide how to organize our list, right? Maybe in this case, since we're only working with one value, right? It would be easier to just use a col, right? So what col will do, we'll take the list, right? Omit a certain value from that list, and then return a new list, a new modified list, right? So you can see here that there's only 5 values left, right? There's 300, 1.5 something something, negative 1.5 something something. It skipped past or deleted this value, right? The third value, then went directly to the fourth value, which was negative 1 whatever, and then 1.5, right? And it skipped the third value because I told it to here under the index, right? I could input multiple values here if I wanted to, right? I could create a list of values of items that I wanted to remove, and that would be fine too, right? And it would reduce the list by even more. But in this way, I actually have pretty good control, because now you can see that if I take the new modified list, right, the list in which the third value had been removed, and I use that my polyline tool, right, with the new inputs, now it's going to draw, right, a new polyline from 0, 1, 2, skip past 3, go directly to 4, and then 5, right? And I want it to complete and create a closed object. So I want to, at the end of the last item, go back to the beginning. So I'm going to change my close value here, which has a false value, to true, right? So I can do that, either manually, or I could use a Boolean toggle, right? That comes from our parameters input and Boolean toggle. And I change that to true, right? So once that's true, you can see that I'm able to draw this shape pretty easily. Now I'm going to hide all of the stuff now that came before for better clarity. And you can see now I have, this kind of 5-sided object, very similar to what I need to draw this half house, right? So the next step, I think, would, might be to extrude that half house in space, right? So let me go ahead, and I'm going to take my polyline here and go to my surfaces. I'm going to say, I want to create a freeform surface, right? So I'm going to extrude along, no, extrude curves and surfaces along a vector, right? So here I can say polyline, and the base will be the object I want to extrude, and then the direction, right, is going to be in the z direction by a certain value, right? So we're going to go back to our vectors. We're going to look for a direction, z, and we're going to use a slider under parameters and slider to give it a factor, right? And again, the slider by default is a bit underwhelming, so I'm going to adjust the values. Let's say 10. Commit. So now I can, scale to my heart's desire, basically, right? Now, the only thing, though, is that in this case, what's happening is that now, after I do this extrusion, I have kind of open ends, right? And we know from our experience in Rhino that if we don't have a closed geometry, we won't be able to use our Boolean tools, right? That's the same here in Grasshopper, right? So our solid difference, right, is still going to fail the same way it did in Rhino if we don't have a solid object, right? So what we need to do is we need to close our geometry in a easy way, right? And if we go to surface under utility, right, we have something that we want to modify. We can choose this one called cap holes, right? And take our extrusion and just use cap holes to very quickly and easily, right, close off the top and the bottom of that extrusion, right? So that'll get us, basically the geometry that we're kind of looking for, right? And then the next step would be to kind of remove this part here on the inside. Now, that's actually going to be a little bit trickier to do than it appears, right? Because we can't simply use a scaling operation. And I'll show you, well, okay, we could, but it won't give us a very good result. So let's say we're going to use that scaling. We would find it under transform, right? So transform, scale, and we want to scale in a certain non-uniform direction, right? Because we don't want the whole thing to scale down smaller. We just scale in a certain direction at different amounts, right? So if we take our object here at the brep as our geometry, and we define the X, Y, and Z scaling differently. So let's say we use a slider for that. So here, so you can see if we were scaling in 3-dimensional simultaneously, we would, we wouldn't be able to cut through fully in the Z direction, right? Because the Z direction, we actually want to maintain the full length. Now with the X and Y, we have some, room to play, right? In terms of how much scaling we want to do. But really, if we, the problem is that you can see that this is right in the middle of our geometry, right? And so long as it's in the middle of the geometry, it's fine. But if we look at our example, you can see that actually the scaling is not done to the middle, it's done to the edge, or this corner here. So if we were to move our plane, right, our base plane, which is the location of our scaling, right, from the center, our origin, to this corner here, well, first we'd have to define where that is, and we can define it simply by doing what? By defining that as a point in space, right? And the point in space would be our, one of these points here, right? So which point was it? Let's see. It looks like point number 5, right? So we're going to go to our sets. We're going to use list item, right? So I'm going to put this list into it, and then I'm going to extract a certain one from it. In this case, I'm going to extract number, actually, I'm going to use a slider here. Extract number 5 so that you can see if I create another panel for you guys, that now there's only one value, right? I only selected one value from this list, and I selected value number 5, which was the last one, right? So it only gave me the 1.5 and then -2 something and then 0, right? It deleted all the rest of them. And I'm going to use that as my center of scaling, right? You can see that now it treats that edge, right, as where the geometry scales to, right? However, what happens is that this proportion then becomes hard to control, right? So you can see that, we're not going to have, completely offset edges, right? You're going to have some tapering going on unless you're able to manage to keep those proportions exactly the same. And even if you did, what would happen is that this would be, maybe thinner and thinner, and then this one would be, thicker, right? Just because that's, it didn't start off as a, um, um, perfect sphere, right? So when you scale it, right, they don't all scale proportionally, right? But for this example, I think this is enough. So you could come in at this point and you could do our intersect again, use the Boolean difference. So we have here the cutting object, right? As well as the overall object. And then if we hide these other ones, you can see that we have what's left over, which is, right, something like this. Right? So that's pretty close to what we see here, although the proportions, right, might be a little bit different. But I think that's, for now, that's fine. And if you wanted to make that, really even all the way around, then you would have to either rebuild the second object, right, with the same proportions, or maybe try it with an offsetting tool, right? But again, it's not as straightforward as you think, so just be aware of that. Okay, so that concludes our half house example, and give it a try, and we'll come back to it. I will come back for the next example shortly. Okay. Okay, so in this next example, first of all, we're gonna skip past a radar slab. You guys, I think you're all bright enough to figure out that radar slab is more or less the same as the half moon tower example, but reversed, right? So if we've completed the half moon tower, I think the radar slab really should be no problem for you guys. So try that one on your own at home. And we'll go on ahead to this one called corner lift. So with corner lift, we're going to start again by looking at the geometry as it stands, right? So we can see here that basically we have a kind of four-sided pyramid geometrically, right? And so it makes sense for us to start and try to build that four-sided geometry first, and then look at how to create this kind of convex shape afterwards, right? So to start with, we're gonna look, like, we use the extrude command already, right? And we know if we go to our freeform tools, right, we have something called extrude to point. So it makes sense that this one probably going to be useful for generating things like pyramids. So we know that the action that we'll take is probably this extrusion. Now, it takes two inputs though, right? It takes a base, which is the curve or surface that we're extruding with, and it takes a point, right? So extruding to a certain location. So let's first create a base, right? The curve that we're going to use to be our base, right? And of course, we could use various tools. Why don't we just go ahead and use the polygon tool? Of course, we could choose a rectangle or whatever as well, but I think this will offer us a little bit more flexibility and be more fun to play around with after. So I'm going to input that polygon as the base, and you can see by default that polygon has a value of 6. I'm going to go ahead and create another slider, and instead of towards the beginning we're getting our slider here, you can also double click, type in a number value, let's say 4, and it'll already automatically generate a slider that contains the more or less the range that you'll probably be using, right? And so I'm going to input that as my segments, and you can see that right away. My polygon is now a 4-sided box, right? And if I change this value, right, I can get all various sizes. Side shapes. Okay, so now that that's set, we have a second input here, which is point, right? So that's simply a point in space, and we know how to deal with that. We can either come into our vector tab and choose to construct a point, or we can also choose unit Z, right? And add a factor using a slider to create, a point in space that, only has inputs in the Z direction, right? For this example, that's all we're interested in. So, okay, so we already have here our kind of pyramid shape. And of course, if we go back and we change the number of sides, you can see that, that relationship still exists and is working appropriately, right? So the next step here would be to take this, which if we look carefully, we see that still has an open bottom, right? And we remember from our previous example, right, that these have to be closed objects in order for those intersect Boolean operations to work, right? So let's go ahead and make sure that we're closing that off as well under Surface, Utility, Cap Holes. I'm going to hide those. So now I have just this geometry visible, right, with the capped bottom. And then I'm going to go ahead and I'm going to use my sphere to act as my cutting object, right? So here I have 2 spheres, basically, one at the top and one at the bottom, in order to generate these 2 round top and bottom shapes. The thing is, I need to make sure that these spheres are, kind of the same size, the right size for that. And right now we can see that, this is far too small what we're trying to do. So I'm going to go ahead and use a larger value for my slider here to define the radius of that sphere. And that'll give me more flexibility. I can adjust the size. And the larger their size, of course, the lower the curvature of the top and bottom, right? However, you can see that when I adjusted the size, it's adjusting at a location towards the middle, right? And I need actually to have this scale towards the point here at the top. So it's going to work. There we go. So I'm going to use this same point that I used here as a Z factor, right? So that no matter how I adjust this, right, that sphere will always follow, right? Will basically, remain parametrically sound, this definition, right? And now I can still, come here and adjust the size of that sphere. Now I know I'll need two of them, so I'm going to go ahead and create a second one first. And then I'll try to adjust that and see if that probably will work, right? So, okay. So now I've generated, all the geometry that I probably will need. And so what I need to do now is to decide what order I want to do stuff in, right? And in this case, it's not really so important, but I will need to do two different actions, right? One is our difference, which we've used several times already. And the other one is intersection, right? In order to get rid of this area outside the boundary, right? So I think what I'll do first is this intersection, right? So the intersection of this circle, or sorry, this sphere and this pyramid will be the geometry that I want to keep, right? And then everything outside of that intersection is not interesting to me, basically. So for the intersection, I will take those two, right? And you can see that it returns to me. Hide this one. It returns to me. Do I still have? Oh, okay. Oh, sorry, I hit the wrong one. It returns to me, right, the shape that's inside that volume, right? But I don't need this one anymore. I can hide that as well, right? So now I have the round bottom. And now I'm going to use the opposite difference, right, with this sphere as a cutting object and this pyramid as the remaining object, or the object to cut from, right? I'm going to hide, again, previous generations. Okay. And you can see there we are left with basically the geometry that we're looking for, right? And again, because I was careful in how I planned it, the relationship of these should, maintain quite well, right? So you can see if I start to adjust some of these parameters, whether it's a square or it's a pyramid or, whatever shape it is, it's still basically follows the rules that are interesting to me, right? And the logic that's kind of inherent in this geometry, right? So in a way, and here's where actually, we discuss the problem or the decision behind whether you should use a parametric modeling strategy or a direct modeling strategy earlier on today, right? And primarily, what we had discussed was the speed, right? Because as you can see, this is much slower, right, than if I had just modeled this directly in Rhino, right? But the benefit of doing it this way is that after I'm done with the model, I still have a lot of flexibility, right? I can still make all sorts of modifications to that geometry, and I can create all sorts of variations, right? All from kind of one definition, right? So you can see in the direct model, I made one thing in like maybe 5 minutes, right? This might have taken me 2 or 3 times longer, right? 10 or 15 minutes, right? But with this, I can generate, hundreds of solutions, right? With that follow more or less the same logic, but have some different characteristics, right? So maybe 6 sides instead of 4 sides, or, the location of where, where that curvature starts or ends, or how big or how small that curvature, all of those things can be modified and all of that is very easy and very fast, right? So you have to decide for yourself what strategy works better for what you're trying to do, right? If you're working on something very specific where you know all the details about the object that you're trying to build, then direct modeling is probably going to be more efficient for you, right? But if you're still in that stage where you're experimenting and you're designing and you know that there's going to be lots of modifications, then maybe, parametric design strategies or workflows are actually going to be not only interesting, but maybe more efficient as well because you still have a lot of flexibility in your design, right? You don't have any kind of fixed constraint. Um, so yeah, so I think that's something really important to keep in mind when you're going about your designs, right? And making a decision about which strategy to take. Okay, so why don't you guys try that out as well? And maybe, you can play a little bit around with some of the parameters and see, get an idea or feel for the different kind of variation that you can create. And then we'll move on to the last exercise for today. Okay, so in our final example for the day, we're going to be looking at this one called flag building, right? So if you remember in the Rhino session, basically the flag building was pretty complicated and time consuming. One of the ones that took kind of a lot of manual labor of like selecting geometry and removing, the different ones that we wanted. And the reason for that is simply because there's more geometry to deal with, and it's kind of more, just the number of components that are required to make it, uh, just numbers higher, right? And that means you have to do more clicking, right? Basically. And I think that's another instance in which you'll find that actually, even if you only had to make one and you weren't worried about creating variations and stuff like that, it might still make a lot more sense to work in a parametric tool rather than in a direct modeling method, right? So as geometry becomes more complicated and more abundant, basically, those data sets become much more difficult to manage by hand, right? So in a way, that's one of the strengths of parametric design as well, is that it allows you to kind of deal with large data sets. So let's look and you can compare with your previous experience in last semester's course and see how you feel. Um, Basically, what we have here is kind of these extrusions, right? And each of these extrusions is more or less like this corner lift example, right? Kind of extruded from a surface or a curve, right, to a point in space somewhere, right? But in this case, they're all going towards a certain point in the center of this sphere, right? So to do that, first we're going to want to define, right, our point in space. So let's go ahead and create that sphere, and it's fine that it's right in the middle, and so we won't modify that base at all. We might want to change the scale of that sphere, so I'm just going to use a slider here to give me that flexibility in the end, although I think it will be on the small side. And then the sphere here, is interesting to us, but we actually want to know kind of where the center of that sphere is as well. So we can use our surface analyze tools, right? And use our volume. So, the volume tool is designed primarily for finding the volume that's inside of a certain geometry, right? But you'll also see here that it also will provide for you the center of that volume as well. So a lot of times when we use the volume tool, as well as things like you can see under the analysis tab, they have area as well, right? It works the same way, right? So if you're working with a two-dimensional geometry and you want to find the area or the center point, right? Oftentimes you'll use this component as well. Um, So the centroid will give us that center point of this sphere, right? Which will also be the point where all those extruded geometries will be going to, right? So how do we, how do we draw, right, those geometries out here in space, those boxes, right, that will eventually come into and be extruded into this point? So the easiest way to do that is to think about this sphere, understanding that it's NURBS geometry like other geometry in Rhino, right? So it has a UV coordinate mapping system on the geometry as well. And so what that means is that we can, subdivide that surface very easily into boxes, right? So if we go into our surface then and we say, okay, I want a second surface, right? Um, it can be a sphere, and I want to make it bigger, right? So that those get generated outside on another layer, right? And get extruded inwards, right? Now, this sphere, though, was the one that we want to actually subdivide, right? So the act of subdividing something is what? Is something that you would find under your utilities tab, right? So for instance, here, we could say, okay, I want to divide the surface. Isotrim. There we go. I want to use my isotrim tool, right, to cut my NURB surface sphere, right, into smaller quads, basically, right? So I'll input that, and then I'll define a domain, right? So what is a domain? Well, a domain is simply a range and the number that you want to define that range into, right? So if we go into our math tab, you can see that we have something called domain here, right? And in domain, it's all different ways of defining ranges of stuff, right? Whether it's numerical, right? Or for flat surfaces, or for three-dimensional surfaces, right? So here you can see that in this case, our three-dimensional object, we're going to use the divide domain 2, right? It says, if you look at the description, it says divides a two-dimensional domain into equal segments. Yes, because all NURBS geometry is technically can be two-dimensional when it gets flattened out, right? Because it's all built on flat sheets. But normally it's the case that when you're going to use that, you're going to be using it on a three-dimensional object like this sphere here, right? So it's a little confusing in that way. Just be aware that that's how they're going to say it. Okay, so the domain that I want to create is of that NURB surface, the sphere, and then I want to be able to modify the U and the V count, right? So right now, by default, it has the setting of 10 and 10. Oh, we might need more. I'm going to go ahead and put in 20. And I'm just going to do, have them even for now. And then I'm going to go ahead and define my subdivision or isotrim in that way. So now you can see that isotrim has generated a new sphere, right? That's composed of quadrants, right? Basically, instead of being one NURBS geometry, one NURB surface that gets wrapped around to look like a sphere, it's 400 NURBS surfaces, right? You're doing the same, that combine to do the same thing, right? So you can think about it basically as a kind of subdivision of the original geometry, right? So if I hide previous, you can see that, okay, now I have something to work with, right? If I wanted to say, if I look at this list, I have 400 objects in this list, and they're all each untrimmed surfaces, right? This is what I'm talking about. When the data set becomes really big, right, it's no longer efficient to do things manually by hand, right? So you're going to want to find a better way to organize that information. And in this case, I think, the 400 that we have here is probably not even enough. So I'm going to go ahead and bump this up to 30 in each direction, right? And that looks a little bit better. Maybe still not enough. That was 900. So if I go to 40, I think that looks a little bit better for what we're trying to do. Okay, so we'll leave it at that. So that's already 1,600 geometries, right? That we just added in minutes. So from there, I want to use again that surface extrude, right? And we're gonna extrude to point here. So these are our geometries, and the points that we're extruding to is the center of this sphere. And you can see now that it's probably very unclear at this point, but all of them got extruded to the center of that sphere, right? Now, if we go back and look at the example here, you can see that, well, there's not that much density, right? There's some space and opening inside there. So we need to figure out a way to remove, right, some of this list of items before we do that extrude, right? So you can see again, this list had 1,600 items, right? So we want to modify this list. And before, when we were modifying the list, we came into our sets tab and we were looking at like using the list item, right? Or in this case, we could do things like use a cull pattern, right? When I used the cull index, right? I said, okay, remove the third point from that hexagon to make a pentagon, right? Right. There's no way that strategy is going to work when we're working with 1,600 items, right? So we're not going to use a culling is a strategy that we're interested in. We do want to remove, but we don't necessarily want to define every single one that we want to move. Instead, we're going to be thinking about that removal process more of a pattern, right? So you can look at some of these other culling methods. Cull nth, right, which removes whichever number of element in a list, right? So if you have a multiple lists, you can remove, for instance, every other item, right? If you set that value to 2, right? So let's say I set this list here, right? And we just compare what happens before and after. You can see that if I set the cull frequency to 2, essentially I'm cutting that list in half, right? So there's 800 values here versus 1600, right? So basically it's removing every other one, right? And if I change this value to say every third one, right? It would reduce it, but not by as much, right? Because it's keeping 2 out of 3, basically. So, that might be one strategy to go about it. But you can see that if you use a strategy like this, you end up with a very, very obvious pattern, right? Because it's like, okay, keep 2, delete 1, keep 2, delete 1, keep 2, delete 1, keep 2, delete 1, etc., right? So, if we wanted to something that didn't have such a strong pattern to it, actually, we could try to randomize that pattern by using the cull pattern, right? Which means that, well, you define a pattern like a true false pattern, right? And then that would reduce the list in that specific way, right? So if you use the pattern, for instance, here, the default is false, false, true, false, false, true, right? Then it's deleting 2 and then keeping 2, deleting 2 and then keeping 2, right? And if I wanted to say modify that pattern manually, right? I could of course come in here and say true, false, true, false, 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 true, and set a pattern manually, right? And see, what kind of results you would get in that instance, right? But really, I think based on, the look and feel of this object, it seems like it's not really in accordance to any specific pattern, right? And when that's the case, then actually the cull that you want to try to use is the cull random, right? So in this case, what it does is it takes that same list of 1600 surfaces, right? And then it performs a reduction, right? And the reduction is according to a certain number of items, right? So that value, of course, if we know that we have 16,000 items, right? We know that this, if we wanted to do a reduction, needs to be quite large, right? If we wanted to reduce it by half, right, then we need to pick a value, right, that's pretty significant. And so here, I'm just going to go ahead and connect this one now instead. And you can see that there is a pattern that's emerging, right? And I can increase the number of that I reduce to make the density less, or reduce, or, if I reduce by less, right, um, that density returns, right? And really, if I wanted to have full control, I would need to set this to have a value range up to the maximum that I have here, right, which is 1600. So you would think that if I, did the reduction to full, right, that gets rid of pretty much everything. And you can see that it repopulates now, right, as I remove that reduction. So from there, there's also this one called seed, which allows us to ask it to recalculate that reduction so that, sometimes we don't necessarily get a reduction that we're satisfied with, basically, right? So it just allows us to kind of randomize that reduction and try it again, basically. Now, what is a better way to do this reduction? I think if we wanted to maintain that kind of parametric relationship, right, this reduction value really should be connected to the number of segments, right? Because you can see here that if I were to modify, right, this value 40, and I changed it to something, smaller, like 20, right? That means that the scale or the range of this slider isn't really appropriate anymore, right? Because I would have anything over 800 would simply do nothing, right? Similarly, if I increased the number of UV counts to 50 or 60, right, then suddenly I would only be able to apply a reduction up until, 1,600 items, but there may be, 32,000 items on that complete list, right? So I wouldn't be able to actually control the entire thing, right? So a better way would be to use our math features, right, to set up a function here, right, so that, we're always working within a certain range, right? But we'll get into that kind of stuff a little bit later when we explore our math functions. But that's just something to be aware of, because I think, one of if we're trying to maintain the flexibility of our parametric definition from the beginning all the way to the end, that means that we have to be careful of stuff like this, right? Because these will break down your definition, right, in the middle if you're not careful, right? So normally, if we are worried about that, we would try to, set up this function separately. Okay, but for now, I think, this is probably enough, and we'll just mix this up a little bit until we get something that looks okay. Let's work with that. So those extrusions are done, and I think this sphere doesn't need to be that big, maybe like this. And then what we're trying to do now is to try to reestablish this kind of outer condition, right? So right now, the inner part looks kind of right, but the outside, you can see there's kind of a box form, right? Where all of these begin from. So all we're going to do is we're going to use I just want to check to see what the geometry type here is. Closed breadth. Okay, good. We're going to use our intersect tool again, right? And we're going to draw a boundary around this area where we're going to keep the geometry and get rid of this kind of outer boundary that looks like a sphere, right? So to do that, we're going to go back to our curves, go to our primitives, surface, our primitives. We'll say do a box rectangle again, right? So our rectangle needs to be defined still. We go to our curves, go to our primitives, go to rectangle, and we can say that's our rectangle. This rectangle doesn't look really like the one that I want to use. So we need to adjust the sizes here. Let's just use some sliders to help us with that. So what we want to do is make sure that we have the right kind of proportions. Box height needs a slider as well. I mean, this kind of looks more like the kind of proportions of the geometry that we're looking for. Okay, so I'll keep that. I'm going to move this box into an appropriate position, right? So I'm going to go to my transform. I'm going to pick move, select this as a geometry. Oops, select this as a geometry. I need to define the movement, right? So I'm going to use something in my vector tab. Let's say, just use a point. I'm going to use 3 coordinates, X, Y, and Z, to position that box where I want it. I may need negative values. Yes, I do. So increase the range of values here to -10 as well. Paste, coordinate. Okay. Hide that. And down a little bit. That looks kind of okay. Yeah, let's say it's like that. Okay. So we have our objects of interest. We're going to take the intersection of those two objects as our final geometry. We're going to hide this stuff. You can see now we're left with this. right? Which should be pretty close to what we're seeing in this flag building example, right? And if I wanted to modify this now, I still have an opportunity, maybe 35. Something broke. Oh, because yeah, okay, so that's exactly what I meant. Because here, when I reduce this, suddenly the reduction number was greater, right, than the total number of values that are available, right? Because there's only 1,224, right? So I know this one has to be less than 1,224 for this to still work. And again, that's exactly what we were talking about earlier, right? We want to have full. Well, I guess I could do this all day. But anyways, if we wanted to have, that parametric relationship be complete from beginning to end, we would want to set this up a little bit differently so that this value wasn't necessarily defined manually, um, but could be defined as a proportion, of our, number here, right? In fact, let me just show you guys how that would be done. So you would come into your sets now, and what you want to do is you want to find your list length, right? So when I modify this, that means that the number of items here changes, right? And the length of the list is influenced by that modification, right? So if I want to always know what that number is, I can use list length, right? And you can see that in this current instance, there's 1,225, right? And so what this will do will also just return me a value, 1,225, which is telling me the number of values that's in this list, no matter how I change it, right? So it's just changing into it a numerical value. And then in order to have this same kind of flexibility, I would use my math function, right? To say, okay, let's say under math, let's say I do a divide, right? So I can take my original number, right? 1,225, divide it by, let's say, 100, and then enter. Oh, slow. Uh, Maybe if I work with it here, it would be better. Still slow. Because of this. Yeah. So if you run into an instance where you're finding that what you're trying to do slows down the operation, a lot of times it's because somewhere down the line there was a certain component or command which was requiring a lot of computation, right? And in this case, you can see here that after you've kind of split up all that geometry and you created all these surfaces, this one here to extrude them all at once, right, was taking a long time, right? Which means that afterwards, when you try to modify it, it can sometimes feel kind of sticky and may not be so ideal. So the way that I usually would do is what I just did here, which was to temporarily disable that component, right? So that I'm only working with a light set of data, right? And I can still tell basically, what that result will be, right? And that actually ends up working better, I think, because, it's much easier to do the subdivision and removal without having to calculate that step back there, right? So here I'm taking this value, 1,225, right? And then I'm saying, well, multiply it by essentially a percentage, right? So now if I wanted to reduce that amount by a certain, by a certain percentage, I could just use a slider from 0 to 1 as a multiplication, right? To help do that kind of random reduction by percentage rather by than by using a specific number, right? That way, if I come here and I modify this, right, this UV count, right, it doesn't affect that relationship anymore, right? So even if I drop it down below, right, 35, right, this still works just fine because it's always a percentage of the total number, right, that we're working with. The only thing that now we want to worry about is maybe if I, I crank that up too high and now I try to reactivate this one, it might crash the computer or take a little bit of time for it to calculate the result, right? But in the end, right, we should get to a position where we're able to, now have a fully controllable parametric definition from beginning to end, right? Okay, so that's it for the week. We'll come back next week and complete the rest of this sheet before moving on to specifically talk about things like, we briefly touched on some of these components, but we didn't really talk, too serious about how all of them work and stuff like that. So, um, once everybody's kind of got their feet wet, I think is a good time to actually get in there and, look at some of these things more carefully. Okay, so that's it for the day. Please, when you're working on these at home, don't forget to redo them. I know it's tempting to follow along during the tutorial and then just, go step by step with me. But try afterwards, to sit down and do it without, watching the video again, because I think uh, following the video is a little bit deceiving because it seems like, okay, that's there, okay, that's there. I know how that works. I know how it's there. But when you actually try and do it on your own without, looking at watching the video, I think that's a, a eye-opening experience, because now you kind of have to train your brain to start, thinking about working in that interface, understanding the logic of the interface and where everything is organized, right? And I think that really, really takes time. And that's why, these first 2 weeks with these exercises, I think is really critical for the development of your Grasshopper parametric modeling skills. So yeah, please do though practice that at home, and we will, I guess, continue on next week. All right. Thank you.